Welcome back to the Massive Loop tutorial series. I'm Tim, and I'm thrilled to continue our journey into bringing iconic anime-inspired mechanics to life using C# in Unity for Massive Loop. Massive Loop is a highly powerful platform for Unity developers looking to create metaverse or spatial computing experiences. It enables you to apply your Unity skills while providing a suite of essential tools such as hosting, multiplayer functionality, cloud persistent variables, and avatar toolkits. These features are available across VR, desktop, and WebGL platforms, making it versatile for various development needs. Massive Loop is trusted by universities, businesses, and Unity game developers alike. In our last video, we explored how to implement a flight mechanic that lets players soar through the skies with the agility and speed of characters from one of my favorite childhood anime series, Dragon Ball Z. Today, we're taking it to the next level. Ever wanted to shoot energy beams out of your hands just like Goku or Vegeta? Well, in this tutorial, we'll be making that a reality in VR. We'll dive deep into creating a dynamic energy beam mechanic, allowing players to unleash powerful blasts from their hands. With that being said, let's get right into the tutorial. First, let's create an object and call it Weapon Controller. Then, let's create a C# script and call it Energy Beam. Click the Weapon Controller game object and add the Energy Beam script to it. Double-click the Energy Beam script and let's start scripting. First, let's start by defining some key elements we'll need for the beam to work. The raycast origin, which is the point where the beam will come from. The hit effect, which is the flashy visuals that plays when the beam hits something. And the beam, which represents the actual energy blast itself. Next, let's add some important variables to control how the beam behaves. Raycast range, which tells us how far the beam can travel. Damage amount, which sets how powerful the beam is. Damage rate, which determines how quickly it deals damage. And finally, trigger cooldown, which adds a brief pause after firing to prevent spamming the attack. Now let's store some internal data the script needs to function properly. Local player represents the ML player. Original beam scale is used to remember the beam's default size. We'll be scaling the beam depending on how far it goes, so keeping the original size helps us adjust it dynamically. We also need some booleans like is shooting to know when the player is firing, can shoot to check if the weapon is ready to fire, and done to confirm when the setup process is complete. Next, let's jump into the start function, which is called when the game begins. In start, we grab the original scale of the beam for later use and add a function called getPlayer to the onPlayer instantiated event. The way this works is that when a player joins the room, the getPlayer function will be called. Now let's create the getPlayer function. This is where we'll connect the beam weapon to the player's hands. First, we create the function and add an MLPlayer parameter to it, so when the function is called through the onPlayer instantiated event, the joining player will be passed into the getPlayer function. Then we check if the joining player is the local player. If so, we store the player into the local player variable we created earlier. Next, let's create a function called findTarget that takes in three parameters: a transform representing the parent, a string, the name of the target object, and a game object, the object we want to attach to the found target. The purpose of this function is to search for a specific child object within the hierarchy of the giving parent, in this case, the ML player, and set the found target as the parent of the game object passed in. The way it works is simple but efficient. The function loops through all child transforms of the given parent and checks if any of them match the provided object name. If a match is found, it checks if we passed in a game object to attach. If so, it sets the found transform as the parent of the object and aligns its position and rotation to the found target, ensuring proper placement in the hierarchy. If the object is not immediately found in the direct children, the function recursively searches within deeper child transforms until it either finds the object or exhausts all possible children. Now that we have our findTarget function, let's call it from the getPlayer function and pass in the local player's transform, the name of the object we want to attach our game object to, and the game object that needs to be attached. Now that we have everything we need, let's start creating the shooting mechanic. First, let's create a function called onTriggerDown. This function will be triggered when the player pulls down the trigger to shoot the beam. First, let's check if shooting is allowed. The can shoot flag ensures the player can only shoot if a cooldown is not in effect. Next, if the player is not already shooting, the beam is activated by setting the beam object to active. Then, is shooting is set to true to indicate the shooting has started, and the shoot raycast coroutine begins, which handles the raycasting logic. Now let's create the shoot raycast coroutine. This coroutine is the core of the shooting mechanic. It handles the continuous shooting process as long as is shooting remains true. First, we set the layer mask. We want our raycast to ignore the player's own layer to avoid any unintended self-interactions, so we can create a mask that excludes layer 10, which is the player's layer. Now, as long as the player is shooting, the function repeatedly fires a ray from the raycast origin in the forward direction. This ray is slightly offset by raycast offset distance to ensure it originates from the correct position relative to the player. When the raycast hits something, several things happen. The hit effect is repositioned to the exact point of impact. This gives immediate visual feedback on where the beam is hitting. Additionally, we adjust the effect's rotation to align with the surface normal of the hit object, making the impact look more realistic. For the beam adjustment, we call the adjust beam function to modify the beam's length so it matches the distance between the ray's origin and the hit point. This ensures the beam doesn't extend beyond where it's supposed to, maintaining visual accuracy. If the raycast doesn't hit anything, we deactivate the hit effect. We then set the beam's maximum length, which is defined by the raycast range, to simulate it extending into the distance. To prevent overloading the game loop, we include a short pause of 0.1 seconds using yield return new wait for seconds. This small delay keeps the game running smoothly without affecting the responsiveness of the shooting mechanic. Finally, when is shooting becomes false, meaning the player has stopped firing, we ensure that both the hit effect and the beam are deactivated. This cleanup step is crucial for performance and visual consistency, preventing any lingering effects when they're no longer needed. Next, let's create the adjust beam function, which is crucial for matching the beam's visual length to the actual distance between the player and whatever the beam hits. First, we reset the beam's position by zeroing out its local position. This ensures that the beam always starts from the correct point relative to the player, avoiding any unintended offset that could make the beam appear disconnected or misaligned. Then, we move on to scaling the beam. We take the distance between the player and the hit object and divide it by the beam initial length. This calculation gives us a scaling factor for the y-axis, effectively elongating or shortening the beam to precisely match the hit distance. By doing this, the beam visually represents the exact path between the player and the target, enhancing the realism of the shooting mechanic. Importantly, we preserve the X and the Z scales of the beam. We only adjust the Y scale, which controls the beam's length, while keeping its width and thickness consistent. This means the beam doesn't get distorted in ways that could make it look unrealistic or out of proportion. It simply stretches and contracts along its length. Now let's create the onTriggerUp function, which is essential for handling what happens when the player releases the trigger and stops shooting. First off, we deactivate the beam and hit effects. By turning off these visual elements, the beam and the hit effect, we immediately remove any visual cues that the player is firing. This instant feedback is crucial for maintaining a responsive and immersive experience, letting the player know that they've stopped shooting. Next, we set the is shooting flag to false. This is a key step in our game logic. By updating this flag, we signal the rest of the system that the player is no longer in a shooting state. This prevents the shoot raycast coroutine from continuing to fire rays or perform any shooting actions, effectively halting the shooting process. Finally, we start the cooldown by invoking the trigger cooldown coroutine. This function introduces a deliberate delay before the player can shoot again. Finally, let's create the trigger cooldown coroutine, which is responsible for introducing a brief delay before the player can shoot again. First, we disable shooting by setting the can shoot to false. This step temporarily prevents the player from firing, ensuring that they can't immediately start shooting again after releasing the trigger. Next, we wait for the cooldown period by pausing the coroutine for a duration specified by trigger cooldown. This is done by using yield return new wait for seconds. This wait time acts as a mandatory delay before the player can shoot again, enforcing a brief pause in the action. After the cooldown period has elapsed, we enable shooting by setting can shoot back to true. This reactivates the player's ability to fire the beam, allowing them to resume shooting as needed. Now in the update function, if done is true, we get the player's controller input. If trigger press 2, which is the right controller trigger, is held down and can shoot is true, then it triggers the on trigger down function. Else, if the trigger input is not true and is shooting is true, then we trigger the on trigger up function. Now let's head back to the editor to complete our creation. Select the weapon controller game object and drag it to the raycast origin field on the energy beam script. For the beam and hit effect, you can use any type of sphere, cylinder, or capsule-shaped object. In my case, I'm using an object I found in a lightsaber asset on the Unity Asset Store. Once you have your effects, drag them to the appropriate fields, and the energy beam mechanic will be complete. Now let's test our creation in the testing environment. It looks like everything works as intended. When I press the right controller trigger button, the beam fires and it's being dynamically scaled depending on the distance from the hit point to the player. That about wraps it up for this tutorial. In the next one, we'll take things a bit further by making the city destructible. Thank you guys for watching, and I'll see you on the next one.